Hello, and welcome to this Fluid Components International, or FCI, webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenter. With us today is Art Womack. Art is the Business Development Manager at Fluid Components International. To read more about Art today, please look at the speaker bio window right next to the main presentation window. And now I would like to pass things along to Art to get this webinar started. So Art, go right ahead.
Thank you for the introduction, Katie. It's good to be partnering with Global Spec once more. I appreciate the opportunity to share some of our flow measurement experience with today's audience. We are anticipating an increased demand for effective and reliable flow instrumentation over the years to come, and it felt like a good time to discuss thermal technology again. I'm going to start today with some of the backstory behind future hydrogen demand, then review a few of the flow measurement challenges associated with this slippery molecule, and wrap up with a quick synopsis of common applications. Get ready for some buzzword bingo as we set the stage. Many of us are probably familiar with the term net zero and have some understanding of how this will impact the global climate and economy. Reducing carbon emissions to the desired levels will be a major factor in the global demand of hydrogen over the next 25 to 30 years. Most countries committed to this agreement are expecting to reach carbon neutral goals by 2050. Net zero is a result of the 2015 Paris Agreement, with the objective of limiting global temperature rise to 1.5 degrees Celsius this century. Many countries, such as the U.S., have implemented initiatives to spur investment in greener technologies. It's interesting to see that even with this push, the usage of fossil fuels that utilize an effective carbon capture and storage system will still be around. These objectives and initiatives are driving us towards a hydrogen economy. Greatly reducing or eliminating the use of fossil fuels for hydrogen production, power generation, and transportation will be necessary to become carbon neutral. One of the more significant challenges faced is building the required infrastructure for the production, transportation, storage, and usage of hydrogen. Why hydrogen? There are a few factors that make this tiny molecule pair so attractive. It is the most abundant element in the universe. Hydrogen has the highest thermal conductivity of any element. It also has a very high specific heat, making this gas a highly effective coolant. Compared to natural gas, the calorific value of hydrogen is 2 times greater than that of methane, which is fantastic. However, it takes 3 times the volume to provide the same heating value. The combustion byproduct is water, so carbon emissions are non-existent when used as a fuel source. In comparison to the carbon emissions of natural gas, is roughly 0.12 pounds of CO2 per cubic foot. The carbon intensity of different hydrogen production methods is another story. From 1975 to 2018, the amount of hydrogen used in industrial processing applications has more than quadrupled. While the percentages for some industries, such as refining, are expected to decrease over time, the overall demand for hydrogen will continue to increase. Various organizations are slicing and dicing the data, but we could be looking at 3 to 5 times the overall demand by 2050 if net zero objectives are met, with the major growth being in power and transportation. So where are we at today with regards to methods of hydrogen production? The color spectrum continues to expand. Other colors now being cited include pink hydrogen, which is electrolysis powered by nuclear energy. Electrolysis specifically from mixed grid solar is now yellow. While brown hydrogen is derived from lignite, the use of black coal is broken out as, surprise, black hydrogen. For today's purposes, we are going to take a quick look at the 5 commonly referenced methods shown here. Steam methane reforming accounts for roughly 50% of today's production. While abundant, using non-renewable natural gas as a feedstock is a long-term concern. Without the addition of CCS, the CO2 emissions exceed what is required to meet long-term carbon neutral objectives. Coal gasification presently accounts for roughly 20% of hydrogen production. Unlike carbon dioxide, the carbon monoxide byproduct does not fall into the greenhouse gas category, even though it has indirect effects on the climate. When syngas is treated further to boost hydrogen production, the additional reaction does result in undesirable CO2 emissions that would require CCS. Like all fossil fuels, coal has its limits as a resource. While not widely used today, pyrolysis could see growth in the future. Like SMR and coal gasification, this method utilizes non-renewable fossil fuels as the feedstock. However, there is no CO2 as a byproduct, only solid carbon, which makes this an attractive production method. While presently accounting for less than 5% of production, the use of electrolysis is currently in a growth mode. This method is extremely attractive since it uses water in place of fossil fuels as the feedstock, and the only byproducts are oxygen and heat. Green hydrogen capacity is expected to increase 80% by 2030. Large investment in this technology is already taking place. Natural gas and coal remain the major sources of hydrogen production for a reason. While its carbon intensity value is attractive, the current cost of producing hydrogen through electrolysis is significantly higher. There will be early adopters of the technology, but it is unlikely that capacity will expand quickly until the costs come down. Adding CCS to gray and brown hydrogen are the more economical choices today. Over the next decade, the cost of green hydrogen is expected to drop significantly. As we move towards meeting net zero objectives, the cost will be more in line with that of blue hydrogen. Between incentives for green hydrogen and penalties for gray hydrogen, we should see an increasing shift in production methods year to year. What does any of this have to do with process instrumentation and thermal flow meters? As more production capacity is added, there's going to be a greater need for gas analyzers and pressure, temperature, level, and flow instrumentation. Therefore, it is going to be important to understand the different measurement technologies available for hydrogen gas and the advantages and disadvantages of each. When selecting a flow technology, it is important to understand how the instrument will perform for any given application. Proper selection leads to fewer complications that could negatively impact process efficiencies or system availability. Let's look at some common requirements and how thermal meters are an attractive choice for measuring the flow of hydrogen and other gases. Most gas flow meter technologies are volumetric. This may not be a concern for general monitoring of gases, but when there is interest in knowing the mass of a gas for stoichiometric purposes or production capacity, they fall short. Hydrogen requires 3 times the volume of natural gas for the same heating value, so knowing the mass flow of a pressurized gas system is important. Volumetric flow meters require additional pressure and temperature instrumentation for compensation. This adds some complexity that impacts your total cost of ownership. Mass flow technologies such as thermal and Coriolis eliminate costs associated with the initial purchase and longer-term maintenance. Let's look at the basics of a thermal flow meter and better understand its operating principles and how it accounts for changing gas densities. Thermal meters are commonly categorized as inline or insertion. In either case, we are dealing with fully welded sensors consisting of 2 sheathed RTDs. There are no moving parts, so these sensors are not prone to wear or leakage. There are no small ports or orifices that can become fouled to the point of making the instruments non-functional. The operating principle revolves around differential temperature. One of the RTDs is heated, commonly referred to as the active sensor. The other RTD remains unheated and is known as the reference. since it is measuring the temperature of the process. Measurement is determined by the cooling effect of the active RTD by the gas molecules. Common misconception is that the reference RTD is measuring the heat dispersed from the active RTD. This is not the case. There are two common techniques for driving the sensor: constant power and constant temperature, which is also known as constant delta T. Constant power is when a fixed current is used to heat the RTD. Power input is the blue line. As flow increases, the temperature differential will decrease. This is represented by the red curve. The change in the differential temperature of the sensor is directly proportional to the mass flow of the gas being measured. Constant temperature is when the current to the RTD is varied to maintain a temperature differential. The amount of current used is proportional to the mass flow. Newer hybrid designs are also available. These hybrids marry both constant power and constant temperature capabilities into a single instrument. Since each technique has its own advantages and disadvantages, hybrids maximize the benefits of both. As discussed earlier, mass flow is best for understanding the amount of gas being delivered or controlling stoichiometric balance of gases used in a process. An example would be the balance of air and natural gas going into industrial burner to maximize efficiency. Looking at the simplified mass flow equation of a thermometer, we see that the gas density is accounted for. Proper calibration of a meter will also address other gas properties that affect the cooling of the active sensor. To better understand how pressure impacts mass flow, here are a couple of cases that will help illustrate the point. The only difference in the process conditions is the pressure. For case 2, the pressure is doubled. As pressure increases, so does gas density. More gas molecules will take more heat away from the active RTD. The result is the mass flow is increased by a factor of 2. Inversely, decreasing pressures will decrease mass flow. Changes in temperature will have the opposite effect on gas density. Also, changes in the process temperature will not impact the gas density as much as changes in pressure. The only difference in process conditions between case 1 and case 2 is an increase in temperature. Increased temperatures result in fewer molecules cooling the heated RTD. Doubling the temperature only reduces the mass flow by 11.5%. Inversely, decreasing temperatures will result in higher mass flow as the gas becomes denser. This graph represents the performance of a thermal flow meter using an air equivalency under actual gas conditions. Other than 100% nitrogen, you cannot lay the curve for any of the other gases on top of the black air curve and expect linearity across the entire flow range using a simple K-factor adjustment. You also start seeing limitations on low or high flow capability depending upon the gas being measured. The best performance is achieved when you calibrate with actual gas under known process conditions. The use of inferred variables in flow measurements is commonly overlooked. This is when a density is assumed without the meter technology being tested on a traceable calibration stand. To save costs, an error calibration might be performed with a linear correction factor applied to offset the differences in the gas densities. Depending upon the technology, these equivalencies don't necessarily account for thermal physical properties of hydrogen, such as absolute viscosity, specific heat, and thermal conductivity. Changing process conditions are not always accounted for when a density is assumed, leading to an incorrect measurement of the actual mass of gas being measured. Industry standards confirm that the best practice for calibrating a flow meter is to utilize the actual gas and mirror the process conditions being measured. Hydrogen calibrations add cost, but those should be easily outweighed by the added confidence in your readings being accurate and reliable. Let's further illustrate why an air equivalency for hydrogen flow measurement is not a good practice. The difference in thermophysical properties of the two gases are extreme. If using a linear correction factor, the results would be highly questionable given the equivalent flow of hydrogen is only 4.56% that of air. Not only does this type of correction impact flow meter performance, it also greatly limits the measurable flow range. Using a hydrocarbon such as natural gas for an equivalency media is not much better. The correction factor is still under 10%. This is just more confirmation that actual gas calibrations are necessary to ensure flow meter performance. Many applications don't require custody level accuracy, so why unnecessarily pay for that level of performance? The typical accuracy of a thermometer is plus or minus 1% of reading with a repeatability of 0.5%. This level of performance has proven to be suitable for many applications in the process industries with the added benefit of a lower total cost of ownership. Regardless of the technology, published accuracy is based on ideal conditions. When calibrated at the factory, ideal straight runs ensure that velocity profiles are fully developed. Often these ideal conditions are hard to come by in the field, especially in larger line sizes. Elbows, valves, and other obstructions within a meter run will result in distorted velocity profiles. Be sure to work with knowledgeable manufacturers that can help you better understand meter accuracy under actual conditions. Most flow measurement technologies have issues when a gas flow transitions between laminar and turbulent flow. For thermometers, this most often can be seen in smaller line sizes. Since the flow is neither laminar nor turbulent in this region, there are calibration challenges associated with the randomness of the velocity profile. This next illustration helps visualize how transitional flow can impact thermal measurements. The blue curve shows the signal from a thermal sensor when flow passes through the transitional zone. The result is a noticeable fishhook in the output. When unaccounted for, linearization of the analog output can introduce an error of plus or minus 10%. Ideally, we want our sensor output to be smooth like the curve in purple. One way to eliminate transitional errors is to restrict calibrations to either laminar or turbulent flow. However, this will reduce the turndown ratio when trying to measure very small mass flow rates. Some available instruments utilize tab-type flow conditioners that create vortices, eliminate error associated with transitional flow, and providing a linear output across a larger flow range. Flow range turndown is also a factor that could impact our measurement. Many applications have varying demands. For example, you may see a very low flow pilot condition to keep a piece of equipment in standby mode that suddenly requires ramping up to 50% capacity or more. Properly sizing and selecting for these conditions requires clearly defined minimum and maximum flow values. As the graph illustrates, there is a significant difference between the more common technologies used. The standard turndown ratio of thermal often exceeds the optional turndown capabilities of technologies such as vortex and differential pressure multivariable transmitters. There are also differences in the flow velocity that a given technology can measure. Some are better at lower and higher flow rates than others. Some are also dependent upon variables such as gas density or Reynolds numbers. It is important to understand the limitations of a technology for any given application. Variations in gas composition will impact the gross calorific value of any fuel being burned. The gas density, which is one of the variables in the simplified mass flow equation, will also change. By properly addressing these variances, we can ensure that our flow measurement is optimized to maintain the appropriate ratio between air and varying blends of natural gas and hydrogen. Given its unique properties, even small variations in the amount of hydrogen will have an impact on measurement repeatability. To help ensure accurate and repeatable measurements, Technologies exist that have the capability of storing multiple calibrations to optimize performance. In many cases, input from a gas analyzer can be used to switch to a calibration that best represents the current gas composition. This approach minimizes inaccuracies related to the specific thermophysical properties of a given composition when compared to a baseline calibration. Several considerations come into play for the safe handling of hydrogen. Hydrogen has an ignition range of 4% to 74% in the presence of air. Its flame velocity is 5.6 feet per second, which is 4.25 times faster than natural gas. Since its combustion is nearly invisible, open flames are not noticeable and can lead to accidental burns if not careful. Hydrogen gas has a low ignition energy compared to natural gas. It's stored at pressures in the range of 5,000 to 10,000 psig. Since it is odorless and colorless, leak detection and proper ventilation is required when stored in enclosed spaces. The small molecule size can lead to hydrogen embrittlement of metal pipelines. For most process industries, it is common for instruments to be installed in Class 1, Div 1, and Div 2 hazardous areas. It is important to select instruments suitable for use in this environment. You will want to confirm with your vendors that the product they are offering has the appropriate third-party approvals. Another item of interest within the process industries is functional safety. This might further limit your options when reviewing different product offerings. You will want to verify with vendors that their product has the appropriate pedigree. Without failure rate data, preferably verified by an authorized third party, performing a suitable analysis of a safety instrumented function that accounts for the logic solver, final element, and sensor is challenging. Safe failure fractions and safety integrity levels alone are not enough to be thorough. Moving into the last stretch of the presentation, we want to share some general information on applications that utilize hydrogen. Some of these applications have been around for a while, and others have just begun to emerge over the past decade or so. There are numerous applications in the petrochem industry that have been around for quite some time, which either consume or produce hydrogen. Depending upon the process, the parameters can vary greatly. Line sizes ranging from 1 inch to 10 inch. Flow rates can be as low as 0.1 pounds per hour and as high as 10,000 pounds per hour. Process pressures in the range of 100 to 1,000 psig. Temperatures from 60 to 200 degrees Fahrenheit. Applications at higher pressures typically require a flow instrument capable of measuring very low actual velocities, especially those in small line sizes. The Reynolds number transitional zone is often a factor that needs to be addressed as well. Hydrogen is commonly used for the efficient cooling of electrical generators, given its thermal conductivity is 15 times that of air. Benefits include increased production efficiency and lower maintenance requirements. Leakage of hydrogen within a generator, housing, or bushing box poses personnel safety issues, given it has a low ignition energy and is difficult to detect. Large enough concentrations can lead to asphyxiation if an area is not sufficiently ventilated or purged. In addition to hydrogen gas detection, mass flow meters for monitoring of top-up gas and the refill line allow for another measurement that can indicate leakage in the system. The most widespread application in the food industry is the production of hydrogenated vegetable oils and fats. This process combines hydrogen with unsaturated compounds such as an alkene or alkyne in the presence of a metal catalyst to produce a fat that remains solid at room temperature. The low density of hydrogen is not easily addressed by some flow technologies. During the transition from natural gas to hydrogen, we are going to see increased demand for gas blending stations. Investment in turbines for gas compression and power generation that can utilize a gas blend is taking place today. Several manufacturers are working towards higher blends above 50% and up to 100% hydrogen. Manufacturers of industrial burners are also looking to capitalize on the use of blended gas. Hydrogen fuel cells are being utilized more for large-scale production of electricity and providing efficient heat for hot water systems. In cases where natural gas is being used as a feedstock to produce hydrogen on site, there are also various emissions that require monitoring. Safety concerns related to hydrogen leaks in closed environments requires the monitoring of ventilation systems. There is a growing demand for the use of proton exchange membranes for electrolysis, given its roughly 80% electrical efficiency. Combined with metal hydride storage in a fuel cell, you have a great source of green energy. Its ability to adapt to dynamic loads is another reason for growing preference and can require flow instruments with broader turn-down ratios. In addition to measuring hydrogen production, safety-critical applications can include the monitoring of ventilation air and deionized water. Having always done something a certain way doesn't mean there is not room to improve. As engineers and technicians, it is important to understand the available technologies to make an informed decision regarding which provides the best results for a given application. When multiple options are available, it is best to dig deeper into the total cost of ownership, not just doing things the same as before. To summarize, utilize mass flow meters instead of volumetric meters to better understand your production capacity or optimize your process control. Evaluate and select a technology that ensures you meet both the high and low flow conditions of your process. Actual gas calibrations ensure the best results. Using a calibration equivalency can introduce additional measurement error. Don't give up on low flow ranges that fall within the Reynolds number transitional zone. Solutions exist for accurate measurement. When multiple technologies are suitable, select instruments that will meet site-specific safety requirements and carry the proper pedigrees. I'm going to hold here a moment if you would like to take a quick screenshot of the summary for future reference. If you would like more information after the webinar or would like to discuss a gas flow meter application, don't hesitate to reach out to us or your local FCI representative. Thanks again for the valuable time you have given us today.
All right, Art, thank you so much for that great presentation. All right, Art, so I'm just going to pick one of our questions out of the queue here to start with. This person is asking, does a thermal meter have minimum piping requirements?
All right, thanks, Katie. Yeah, if, as mentioned in the presentation, typical recommendation for us is 20 diameters upstream, 10 down. Now that's going to vary depending upon manufacturers. Everybody's got their own opinion of what that straight run should be. But the key thing here is to allow for that fully developed velocity profile. If you get anything less than that, you're going to see some inaccuracies. The extent of that inaccuracy is really going to be based on the type of obstruction, such as a valve or an elbow, and its proximity to the meter location.
All right, thank you so much for that answer. So moving on here in our queue. All right, this person is asking, are there concerns using heated sensors since hydrogen is highly flammable?
Always a question that comes up from time to time, regardless of which type of flammable gas you might be dealing with. But, the answer here is really not at all. We've been calibrating thermal flow meters in pure hydrogen and hydrogen hydrocarbon blends for decades now. The amount of heat transfer to the gas is not sufficient to ignite the gas itself. And the other thing is you also have to have the presence of air or oxygen in sufficient amounts. And this is not typically the case when we're dealing with these types of process measurements.
All right, thank you so much for that answer, Art. So for all of our attendees, if you have a question today, you're going to use that Q&A window, click submit, and enter your question or comment right into that box. I also wanted to point out some of the resources we have listed in our resource list. There's 4 different items listed in there, one of which is a PDF of today's PowerPoint. And then there's 3 other documents in there that you can take with you today. So go ahead and take a minute to look at the resource list, download anything that interests you before you leave today. All right, Art, so our next question here. Okay, this person is asking, how is high velocity of H2 as process fluid considered during calibration? Are the present calibration facilities H2 ready?
That's a great question because, again, it's one of those things you really got to look at when dealing with manufacturers and the calibration of any type of flow meter for hydrogen. When done properly with the calibration facilities, using an actual gas, your pressures, temperatures, and actual velocities are really part of that calibration itself. So it really comes down to your confidence in that manufacturer and their ability to properly calibrate the instrument.
All right, thank you so much for that answer. So for our attendees, we do have a lot of questions in our queue. If you do not hear your question being asked, we will reach out to you following today's webinar since we don't have time to do everybody's question, but we do appreciate all of the questions. So go ahead and keep entering those in and we'll get through as many of them as we can. All right, Art, next one here. What kind of question should I ask a manufacturer to ensure a flow meter is properly calibrated for hydrogen?
Capability. So, questions we typically like to see are, and think you should ask about are how applications are evaluated, given all your process conditions, can that measurement be made with the technology? The type of calibration, how is it performed? Is it going to be an actual gas? Is it going to be some type of equivalency method? Things of that nature. And, others get into, again, the question on straight run. Is it going to have an impact on my, accuracy of my reading? Am I really going to read close to the published manufacturer spec, or is it going to be something else? And then you get into the appropriate certifications if you've got any requirements there. Those are just a few of the key ones, And, if you like, ourselves, if you send us a message to eFlow, we've got a brochure that talks about, selection of thermal flow meters.
All right. Thank you so much for that answer. And then just a quick reminder to attendees, we also have a survey, which is going to pop on your screen at the end of the webinar. That survey is located along the bottom of the attendee console as well in the resource widget. So that is listed along the bottom of your attendee console. So you can feel free to fill out any of those questions at this time and grab those items out of the resource widget. All right, Art. So next question here. How is high velocity of H2 as process fluid considered during calibration? Are the present calibration facilities H2 ready?
Again, I'm not sure if we answered that one yet or not, but those type of things, velocities, pressures, temperatures, your manufacturer should be taking that into account in the calibration process. And like stated before, it's always a best practice to calibrate in actual conditions as close as possible. I can only speak for ourselves, but we do have hydrogen capable calibration here at our own facility. There are no third parties involved.
All right, great. Thank you so much. All right, next one here, and I apologize if some of these are similar to each other. But the next one here, for small bore pipe work, 1-inch line, is it better going up a line size to get a better Reynolds number for accuracy? Example 2.
That one's, again, you got to talk to your manufacturers because, yes, if you go up in line size, it will change where your Reynolds number is impacted. So, Typically, if you want to get a lower range, you'd want to go maybe down in line size to get the velocity higher and above the Reynolds number. You got to keep in mind, you go larger, that actual velocity is going to drop, and then you'll be on the low end. It really comes down to what's critical, a high flow or a low flow measurement. Again, and there's solutions out there that, even with a 1-inch line, if you're transitioning through that zone, you can still do it. You just got to look at, what the overall result is. Again, focusing on that min-max flow. And with those solutions, your accuracy should be as good as if there wasn't a transitional zone there at all. Hope that answers the question.
Right. Thank you so much, Art. So we do have time for a couple more questions. So we're going to move right into this next one here. How developed and proven are sealing materials in H2 application?
I'm not sure I fully understand that one, Katie, but I think what we're getting at is, when you're installing an instrument into the process, what kind of sealing methods. Typically, these applications, you're going to look at products with, either flange connections or, a compression fitting maybe with a metal ferrule, because your concern there would be any kind of loosening of that connection, potentially, hydrogen leaking into the atmosphere. If that's not the answer, I can get back to them later.
Yeah, I was just going to say, Art, thank you for that. For anybody, we can follow up on certain questions, and we will follow up with everybody following the webinar that asked a question. So we can always get you more information at that time. Okay, Art, next one here in our queue. Other than petrochem, concern for hydrogen embrittlement can be real. What is needed to address this problem? Special piping or what?
Boy, that's a good question. That's one where we're not necessarily the experts in piping. I think you got to look at the other sources in the industry to understand what the future needs may be. I just know from what I personally have heard is the current infrastructure for natural gas, there is a concern when hydrogen perhaps gets into higher percentages if it's blended with natural gas. But again, I would recommend further research.
All right, great. Thank you so much for that answer. All right, Art, next one here. What is the optimal position for placing a flow transmitter after or below an on-off valve?
Good question. I think one of the things we got to look at is what type of valve it is, because that'll play a role. Some valves are more restrictive than others, even in an open position. A butterfly valve, is going to have some impact on, the flow profile going into the meter. Typically, butterfly valve type items, not a huge influence. What we see is probably a bigger influence is a control valve that is modulating, not necessarily on off. If something's modulating and it's upstream of the meter, it can introduce a very large error depending upon its proximity to the meter itself. Guidelines, I think, within the industry is preference is to put those types of control valves downstream, and that way it minimizes the influence.
All right, thank you so much for that answer. So just a quick reminder to the attendees, if you don't hear your question being answered, we will reach out to you following the webinar. Using that Q&A window, typing your question or comment in there and clicking submit will get your question placed in our queue. All right, Art, next one here. The process connection for the meter looks to be a screwed connection. Have you had issues with leakage or high pressure installation? Example, less than 20 bar?
Again, when you look at process connections, I think, you've got that safety factor in there. Typically, when you get into higher pressures, you'll see less use of threaded connections, whether they be female or male MPT. You'll see maybe a fixed,
MPT connection where there's no gland involved and it's, fixed length, you'll see a lot of flange connections. Typically you're going to see more flange connections in these higher pressure hydrogen applications.
All right, Art, thank you so much for that answer. Okay, moving to our next question here. What specification or standard governs the calibration of gas flow devices?
Typically, there's several, but the more common ones you're going to see, and you might want to check with your manufacturer of any instrument is. You'll see NIST traceability. You'll see reference to IEC. I believe it is 17025. Again, traceability on their calibration equipment. Make sure it's maintained properly. The primary, flow measurement devices are kept up to date, calibrated because they need to be such a higher accuracy than the meter under test. Those are the two main ones we see as far as driving, support of a manufacturer to ensure calibration of an instrument.
Right, thank you so much. And then just a quick reminder to the attendees about the resources that we have listed in the resource widget. There are 4 of them in there today for you, one of which is a PDF version of this presentation so that you can continue to look at it and follow along. We also will have an on-demand period. So for 90 days following today's webinar, you will be able to come back here and watch this again and be able to download any of those resources and ask any questions as well during that 90 days. All right, so it looks like we have a couple more questions in our queue, but we are hitting our time limit at this point. So we're going to start to wrap the webinar up in just a minute. For anybody that did not have their question answered, as I've mentioned a couple times, we will reach out to you following today's webinar. If anybody has a last minute question they want to pop into that queue, feel free to do that right now, and we will get back to you following today. So Art, I want to get back over to you and say thank you so much for a great presentation and for taking so many of our attendees' questions. You did a great job and we enjoyed having you.
Thank you, Katie. Always a pleasure.
So again, a huge thank you to Art and thank you for all of our attendees for taking time to attend this webinar event. Take care and we will speak with all of you soon.